We are going to discuss some aspects of continuous time Markov chains, like stationary distributions and limiting distributions. We are going to consider a random process, and we assume that we have a countable state space uh, S. If x0 equals I, then xt stays in state I for a random amount of time. Let's call it t1, where t1 is a continuous random variable. At time t1, the process jumps to a new state, let's call it j, and it will spend a random amount of time, and the time it spends in this state j, let's call that t2. Again, it is a continuous random variable, and so on and so forth. These continuous random variables, which we have called t1, t2, t3, and so on and so forth, follow an exponential distribution. And the probability of going from state I to state j is denoted small p I subscript ij. To make any prediction about the future, it should not matter how long the process spends in each state, and therefore we must have something called a memoryless property. The exponential distribution is the only continuous distribution with this property. So to make a note of that, exponential distribution is the only continuous distribution with this property. The time that a continuous time Markov chain spends in a certain state I is called holding time. And it will follow an exponential distribution where these lambda i's are non-negative real numbers. These lambda i's are your holding time parameters. Therefore, a continuous time Markov chain has two components. The first component is known as the discrete time Markov chain, which is better known as the jump chain. That gives the transition probability p small p subscript I j. And the second component are the holding time parameters. Lambda I that control the time spent in each state in the jump chain. Let's consider a simple example. So a Markov chain with two states S mean 0 and 1 with holding time parameters lambda naught equals lambda 1 equals lambda being greater than 0, and we wish to first of all draw the state transition diagram. For the jump chain. And the second thing we want to do is to find the transition matrix, and let's call this transition matrix P and T. Yeah. So we wish to find P T transition matrix for this jump chain. First, note that there are two states in the chain and none of them are absorbing. Why? Because an absorbing state would mean that the holding time parameters equals 0. But we are told that the holding time parameters are greater than 0. So we have states which are non-absorbing states. And just to clarify, we have absorbing states if and only if the holding time parameters are equal to 0. The jump chain must therefore have the following transition matrix. Right? So P will equal so the probability of going from state 0 to state 1 is 1, and so on for state 1 to state 0 is also 1. So this is the state transition diagram of the jump chain. To repeat, we go from state 0 to state 1 with probability 1, and from state 1 to state 0 with probability 1. The reason for that is again that the holding time parameters are non-absorbing. Now we wish to find the transition matrix. We proceed as follows. First of all, notice that the Markov chain has a simple structure. So let's begin by computing P naught naught. Now the time between each transition is e to the lambda, since we are using the exponential distribution. And going back, P naught naught by definition is defined to be for all t in the interval which equals the sum of n equals 0 to infinity we have that p naught naught of t equals e to the minus lambda t, then the sum from n equals 0 to infinity lambda t the sum being defined as e to the lambda t plus e to the minus lambda t over 2. So we have that equals a half e to the minus 2 lambda t, which also happens to equal p1 t. p naught 1 of t equals 1 minus p naught naught t, which equals p1 naught t. So we have that p naught 1 t equals p1 naught t equals a half minus a half e to the minus 2 lambda t. Therefore, the transition matrix for any t greater than or equal to 0 is given by thus we have solved the question. We quickly note the properties for the transition matrix must satisfy for a continuous time Markov chain. So the first property it must satisfy is at p naught is equal to the identity matrix i.e. p or naught equals the identity matrix. The second property it must satisfy is that the rows of the transition matrix must sum up to 1. That is the sum of the transition probabilities along each row must sum up to 1 for all t greater than or equal to 0. And the third property is that for all s and t greater than or equal to 0, the probability of S plus T equal the probability of S times the probability of T. We now wish to look at how to compute limiting distributions for continuous time Markov chains. As our first example, we wish to consider a continuous time Markov chain that has the following jump chain, and we assume that we have the following holding time parameters. So lambda 1 equals 2, lambda 2 equals 1, and lambda 3 equals 3. And we wish to find the limiting distribution for this Markov chain. First of all, notice that the chain is irreducible. The transition matrix of the jump chain is given by solving the following system of equations. We can find the stationary distribution for the jump chain. We find the following relations. So we have found that the stationary distribution for the jump chain is to find the limiting distribution from the stationary distribution. We need to use the following formula, which is where lambda j and lambda k are the holding time parameters. So we have the following. Therefore, we conclude that is the limiting distribution of the continuous time Markov chain. We now wish to consider a continuous time Markov chain with the following jump chain, but with holding time parameters lambda 1 equals 2, lambda 2 equals 3, and lambda 3 equals 4. Well, notice again that the chain is irreducible, and now we follow the same steps. We first of all write down the transition matrix for the jump chain, which in this case is equal to the stationary distribution is found by solving the following system of equations. And the stationary distribution is found to be again by using the formula and the information given to us about the holding time parameters and the stationary distribution which we have just found, we find that the limiting distribution for the Markov chain in consideration is so. To conclude, we have found the limiting distribution of the continuous time Markov chain to be